All right, just like last chapter, I'll do some bonus multiple choice review problems with you. Now, instead of getting these problems from, usually there's like 3 tests that I can choose from the textbook company. Last chapter, that's what I did, was I used a test that I didn't end up using to give you for the chapter test. I'm going to use the multiple choice questions that are at the end of the chapter in the book as the practice test. And I have one additional question, which is from a test that I am not going to give you. So you will get a little bit of a feel for that. I thought I would throw it in there. So these problems are in the book if you want to follow along with me, or if you just want to try these out on your own, just looking at the video, that is fine. In your book, it is on page 597. So the first one says, an opinion poll asks a random sample of adults whether they favor banning ownership of handguns by private citizens. A commentator believes that more than half of all adults favor such a ban. The null and alternate hypotheses you would use to test this claim are la la la. Now, we can look through these options before we even start to see which ones are definitely wrong because they're written wrong in general. The main things to remember here are that the null hypothesis, and since obviously we're dealing with proportions here, it's always about the population proportion, just p, and that p needs to equal some value. So we can first start going through here and saying, well, which null hypotheses don't say p equals? So A, hey, this says p hat, so this is wrong. This says p equals, p equals, p equals. P is greater than. We can't have a greater than sign in the null hypothesis, so that one's wrong. So 0.5, 0.5, 0.5, we know that we're saying 0.5 because we were saying whether adults favor banning handguns. And the commentator believes that more than half. So there's our half, our 0.5. So alternatively, we know that P, now it says more than half. So we are probably more than likely going to be using a more than, a greater than sign, and using 0.5. So this one uses the less than, this one uses the not equal to. Here is the only one that truly ends up matching. Second question. You are thinking of conducting a one-sample t-test about a population mean mu using a 0.05 significance level. You suspect that the distribution of the population is not normal and may be moderately skewed. Which of the following statements is correct? So first off, you should not carry out the test because the population does not have a normal distribution. Now, it is typically nice if the population has a normal distribution, but it doesn't have to have a normal distribution. So that's not necessarily the case. B, you can safely carry out the test if your sample size is large and there are no outliers. Sample size is large, which is typically a nice thing, and there are no outliers. That's typically a nice thing. So let's keep this one for now. Let's see if we can eliminate our other options here. You can safely carry out the test if there are no outliers, regardless of the sample size. Well, it's good to have no outliers, regardless of sample size. Well, let's kind of keep this because it kind of seems like B and C are basically the same, except this one's talking about a large sample size, and this one's saying regardless of our sample size. So, all right, let's go on. You can carry out the test only if the population standard deviation is known. Population standard deviation, that's sigma. Do we really need to know what sigma is to do a t-test? No, you really don't. That's just unnecessary altogether. Now E, the T procedures are robust. You can use them anytime you want. Now this term robust, I kind of skipped over from last chapter. Robust just means, how can I put this? That T procedures, the T distribution altogether, it works very, very well. So here's the definition I got here. The T procedures are relatively robust when the population is non-normal, especially for larger sample sizes. The T procedures are not robust against outliers, however. So this says the T procedures are robust. You can use them anytime you want. Well, in the definition, it just says except in the presence of outliers. So this one's going to be wrong. don't worry too much about this idea of robustness. I will not put a question on the test related to that since we didn't exactly cover it. Now, we're down to B and C here. What do you think would be the better option here? Having a large sample size, or who cares about the sample size? I would personally lean more towards, if I had the option, of having a large sample size. That's what I would prefer to go with here, especially since it says our population is moderately skewed. Okay, now that doesn't mean it's strongly skewed, but it's moderately. A larger sample size will turn that moderately skewed population distribution into definitely a clear, approximately normal, or an approximately t distribution due to the central limit theorem. So here, even though they're talking about no outliers, there may still be skewness there. And skewness will start to go away with a much larger sample size due to the central limit theorem. So again, I would pick B as the final answer. Number 3, to determine the reliability of experts who interpret lie detector tests in criminal investigations, a random sample of 280 such cases was studied. The results were right there. If the hypotheses are H naught, suspect is innocent, versus HA, suspect is guilty, then we could estimate the probability that experts who interpret lie detector tests will make a type 2 error as... So first let's talk about a type 2 error. Now we haven't really seen a problem like this before. I wouldn't anticipate such a question being on the test, but for those maybe considering the AP exam, this would definitely be a type of question you might see on the multiple choice. So let's go through it. It's not going to take too long here. A type 2 error, that is when we fail to reject the null hypothesis, but we should have. So that really means in this specific case here, that means if we fail to reject, that means we said innocent, but really they're guilty. Innocent, but really guilty. We thought, we'll say that. We thought innocent, but really guilty. Okay, so we thought innocent. Here's the examiner's decision. The examiner thought that the person was innocent, when in fact, here's the suspect's true status of guilt. There's 15 of those people. So 15 out of, and we would consider our total number of guilty people, because technically we incorrectly, out of these 140 truly guilty people, we thought 15 of them were innocent, and that is our type 2 error. So 15 out of 140, that matches up with C. Again, don't worry too much about this question being on the test, but definitely it would be a nice thing to be able to know. Number 4, a significance test allows you to reject a null hypothesis H naught in favor of an alternative HA at the 5% significance level. What can you say at the 1% level? So let's see. We were allowed to reject the null hypothesis at the 5% level. So that means our p-value, oh, if I can spell p-value right here. That means our p-value, whatever it is, it had to be less than our alpha value of 0.05 or 5% to reject. Okay, so our p-value had to be smaller than 5%. What can we conclude at the 1% level? 1%. Well, if we rejected at the 5%, does that mean we can automatically reject at the 1%? Let's talk about some scenarios here. What if I picked a p-value of 0.03? That's less than 5%, and I would reject. Would I reject at the 0.01 level? No, we wouldn't reject. We would fail to reject. But I could also look at the scenario, so that goes with that. What if I had picked 0.001 and compared that to an alpha of 0.01? Then we would reject that. So it really depends on our p-value. If it's going to be in between 1 and 5%, or if it's going to be less than 1%. Did they really give us enough information in this problem to do it? They didn't. So our answer is E. The answer can't be determined from the information given. We would need to know a little bit more about our p-value. Number 5. A random sample of 100 likely voters in a small city produced 59 voters in favor of candidate A. The observed value of the test statistic for testing the null hypothesis that p is equal to 50% versus the alternative that it's greater than 50% is, well, here's where we just are using a hypothesis test for a proportion. And here's where we would have p hat minus p naught over square root p naught times 1 minus p naught over n. Okay? Now, if I just start with, let's say, one of these spots, n is my sample size, and that is 100. Notice, 100, 100, 100, 100, 100. We're good. Let's see, where else do we maybe have some differences? P hat. That's our sample proportion. What value did we get from our sample of 100? We got 59. Now, p hat is not 59, it is 59 out of 100, which is 0.59. So p hat's 0.59. So 0.59, check. 0.59, check. 0.5, uh-oh. 0.5, uh-oh. 0.59, check. So we've eliminated so far just C and D. So we move on. P naught. What is this P naught value? The P naught value, if you remember, comes from our null hypothesis, which is 0.5. So that needs to be 0.5. Check. Good. Check. Good. Check. Good. Okay. So we still got everything there. And we're going to use the same P naught value down here in the denominator. They did not. They used p hat and 1 minus p hat. Here they used it. Okay, sweet. Here they used it. Holy crap, how can I have two answers that are the same? One little difference. Did you guys catch it? This says z equals, this says t equals. Now, since we are doing proportions, proportions are always z-scores. So B is our answer. T we only use for mean problems. So they were trying to mix us up with our mean and our proportions. Number 6, a researcher claims to have found a drug that causes people to grow taller. Please, I want some more. I'd always love to be like 6'6". That'd be awesome. The coach of the basketball team at Brandon University has expressed interest but demands evidence. Over 1,000 Brandon students volunteer to participate in an experiment to test this new drug. 50 of the volunteers are randomly selected. Their heights are measured, and they are given the drug. 2 weeks later, they failed a drug test, and they were kicked off the team. No, but 2 weeks later, their heights were measured again. The power of the test to detect an average increase in height of 1 inch could be increased by, so the power of the test to detect an average increase could be increased. We want to increase the power of the test. Now, there were 2 things I told you from the videos about how to increase power. Number 1 was to increase our sample size. And number 2, the lesser known, was to increase your alpha value. So A, using only volunteers from the basketball team in the experiment. Nope. Using alpha equals 0.01 instead of 0.05. So going to 0.01 from 0.05, this is a decrease in alpha. And we just said we want to increase it. Using 0.05 instead of 0.01, oh, we are increasing alpha now. So this works. But let's make sure these other 2 are wrong. Given the drug to 25 randomly selected students instead of 50, oh, they are decreasing the sample size. And we say we want to increase it. So it's not D. Using a 2-sided test instead of a 1-sided test doesn't really matter that way. So forget that. It is, in fact, C. Number 7. A 95% confidence interval for a population mean mu is calculated to be 1.7 to 3.5. Assume that the conditions for performing inference are met. And again, when they say inference, they just mean, like confidence intervals is an inference procedure. Hypothesis testing, that is an inference procedure. What conclusion can we draw for a test of mu equals 2 versus it's not equal to 2 at the alpha equals 5% level based on the confidence interval? Well, anytime they give us the confidence interval, we just need to ask ourselves, is 2, mu equal 2, in our confidence interval? So is mu equal 2 in this confidence interval? And we would say, yeah, 2 is in between 1.7 and 3.5. So it is a possibility for mu. We would not want to reject this value. So basically we would say we would fail to reject the null hypothesis. So let's see, what does it say here? What conclusion can we draw? None. We cannot carry out the test without the original data. No, we just said we can do it here, so we're good. None? No, we said we could do it. None? No, we said we could do it. We would reject H naught at the alpha equals 0.05. Yeah, because since we're using a 95%, and here they gave us 0.05 level, yeah, well, but one little thing here, this does say reject. We did say fail to reject, so no. We would fail to reject H naught at the 5% alpha level, and that's exactly what we did. So the answer is E. Number 8. In a test of P equals 0.4 versus it's not 0.4, a random sample of size 100 yields a test statistic of 1.28. The p-value of this test is approximately equal to. So once we got our z-score, we needed to draw a curve. And 1.28 really means 1.28 standard deviations above the mean. So I'm going to estimate that that is about right here. And I will shade. Now notice my alternate is not equal to, so I need to shade not only this, but then I need to go symmetrically over to the other side to negative 1.28 and shade to the left of it. Now, we have two p-values that we're going to have to combine together. Let's just go ahead and figure out this one here. Since we're using z-scores, we get to use normal CDF. We don't use t-CDF because we're not using t-scores. So our lower bound is 1.28. We are going up to infinity, no degrees of freedom since we're using normal CDF. So normal CDF, let's see, 1.28 up to infinity gives me a p-value of 0.1003. Now, notice, is basically 10% an option over here? Oh, it is. Awesome. That's the answer. Brr, no, it's not the answer because we have to double this because we have two tails due to our alternate hypothesis being not equal to. So it's not really 10%, it's really 20%, aka answer D. So make sure you really notice the alternate hypothesis sign. If it's less than or greater than, don't double the p-value. If it's not equal to, you got to double it. Number 9. A simple random sample of 100 postal employees found that the average time these employees had worked at the Postal Service was 7 years, with a standard deviation 2 years. Do these data provide convincing evidence that the mean time of employment, mu, for the population of postal employees has changed from the value of 7.5 that was true 20 years ago? To determine this, we test the hypothesis that mu is 7.5 versus it is not equal to 7.5 using a one-sample t-test. What conclusion should we draw at the 5% significance level? Well, number one here, we could carry out the entire test, okay? And we could do all the calculations by hand. Since we're doing a mean level problem here, we'd have to find a t-score and do x bar minus mu naught over s divided by the square root of n. We'd get that number, and then we'd have to do t, CDF, and yada, 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 and boom, there's our p-value. Oh, and then we got to double it because we have two tails because the alternate hypothesis is not equal to. Or this is where you can use the calculator, okay? So if you haven't looked at this yet, and I kind of had a little blurb for this at the end, so let me just jump ahead real quick. How to do hypothesis tests on your calculator. On the bottom of the front page of your notes, I have this little box here. So a one sample mean t-test. Read the technology corner on page 573, and it will show you how to do it. Now let me just jump back to this problem and let's actually do it. Now, if you go to your calculator and press Stat, go over to Tests, and we need to do a t-test. So option 2 is on my calculator. Now, it says input data or stats. Well, we don't have any data to work with, but we have some statistics to work with. So make sure that stats is highlighted and press enter to select it. Then your first option should say, it looks like a mu with a little box, but it's really mu naught. And that is our null value. So you need to put in 7.5 for mu little box naught. And then x bar, that's our sample mean. Well, from our sample, our 100 employees, we found that it was really 7 years. So for x bar, so here, I'll put this here. That, you need to put 7.5. For x bar next, we're going to put 7. Below that, we have S sub x. This is our sample standard deviation, which they set up here was 2 years. So put 2 for that. Next up is N, our sample size, which they told us was 100. And then below that, it says mu, and then not equal to mu naught, less than mu naught, greater than mu naught. We just need to select the appropriate alternate hypothesis, and it was not equal to, so just make sure that this option is highlighted. And then select calculate, press enter, and all of a sudden it will say t-test, mu greater than, why did it say greater than? That's weird. Well, let's see. Let me just double check here. Gives me a p, well, this isn't right entirely at all. Let me redo this. What's going on? T-test, t-test. Da 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 da. There we go. There we go. Now I get a p-value. It says p equals 0.01406. So at the 5% level, this is our p-value. Is it less than alpha equals 0.05? Yes, it is. We would reject the null hypothesis. Now notice, we just did all of that work that we would normally have to write out in our calculator. And since this is a multiple choice question, you don't have to show any work. So do it in your calculator. Be smart about it. Learn how to do it. Do a few examples. So we found we would reject the null hypothesis, which means that there is convincing evidence. We do have enough evidence that the mean working time for the postal employees has changed. Not convincing. We cannot draw a conclusion. The sample size is too small. That's ridiculous. So there is convincing, there is convincing, is convincing. Let's see, what are the main differences between these things here? That the mean working time with the Postal Service is still 7.5. Well, no, we would conclude that it's different than 7.5. That the mean time is now 7 years. Well, we didn't really conclude with the alternate hypothesis that it's really 7 years. We just said that it's not 7.5. And not 7.5 means that it has changed from what it used to be as our null hypothesis. So A is really our correct answer here. And the last problem. This one is not number 10 in your practice test in your book here. So this one you do not have, okay? So it says the recommended daily calcium intake for women over 21 and under 50 is 1,000 milligrams per day. The health services at a college are concerned that women at the college get less calcium than that. So they take a random sample of female students in order to test the hypothesis that mu is 1,000 versus it's less than 1,000. Prior to the study, they estimate that the power of their test against the alternate, that mu is 900, is 0.85. Which of the following is the best interpretation of this value? Now, this isn't a typical type of problem here, but notice our alternate hypothesis is that mu is less than 1,000. Well, there are many numbers less than 1,000. So what they did was they just picked a value that is less than 1,000, and they picked 900. Now, 900 is 100 below 1,000. The farther we get away from 1,000 and below 1,000, the power of our test increases closer and closer to 100%. And one thing to remember here is that the definition of power is that it is the probability that we basically correctly reject the null hypothesis. Okay, you pretty much need to know that definition because there will probably be some sort of question related to power on the test. So, which of the following is the best interpretation of this value, this 0.85 power value? It is the probability of making a type 2 error. No, actually type 2 error would be 1 minus this 0.85, which is 0.15. So no, that's wrong. The probability of rejecting the null hypothesis when the parameter value is 1,000. Well, we are good here. It is the probability of rejecting the null hypothesis. But when the parameter value is 1,000, well, 1,000 is the null hypothesis. So they're saying reject 1,000 and conclude it's 1,000. Well, that's contradictory. That can't be right. Probability of rejecting the null hypothesis. So yes, let's reject when the parameter value is 900. That is right, because if we're rejecting the null hypothesis, we are going in favor of the alternate. And they are giving us a specific value for the alternate in this case, which is the 900. So the probability of rejecting the null hypothesis when it's really 900 is our 85%. So it is C. And now D and E both say that it is the probability of failing to reject. And power is not about failing to reject, it is about rejecting. So that's why those two are wrong. So again, the very last little blurb I have here, if you haven't saw how to do hypothesis tests on your calculator, please go look on pages 555 to 556 to see how to do a hypothesis test for proportions, and then page 573 for how to do a hypothesis test for means. And that is all. Good day, adieu. I hope you learned something, and good luck on your test.